Hello. I'm going to briefly go over the information that we would have talked about in class today, Tuesday, October 11th. This information should help you with the review tomorrow, and you can use it to help you with your index card for your test on Thursday. If after going over this and looking at the review tomorrow, if you still have some extra questions about it, please send me an email and we can figure out a time to either talk in the office hours session or to discuss things via email before you take the test on Thursday. So let's get started here on acceleration, accelerated motion, and the review for accelerated motion. So some notes here. First of all, let's look at the top left-hand corner. If you are having motion that is in the positive direction and you are speeding up, your displacement time graph is going to look like this, velocity time graph, and that should be a straight line, sorry, and acceleration time graph. These are what they should be looking like. And if you have something that looks like this, then you know that x is proportional to t squared. That sign there means proportional. So x is proportional to t squared, and v is proportional to t. So that's the equations that you would have with them. If you have a situation where the object has positive direction but is slowing down, these are the three associated graphs. It's the x slows down, the v is again a straight line but decreasing, and acceleration is a horizontal line. If the object is moving in the negative direction, sorry, I forgot to write the word direction there, moving in the negative direction and speeding up, its graph will look almost like the mirror opposite of the positive direction slowing down. The speed will be increasing in the negative direction, and acceleration will again be negative. If we have an object going in the negative direction but slowing down, it will look like this. Velocity will be decreasing towards zero from a negative value, and acceleration is positive because it's negatively slowing down. If you have something that has continuous parabolic shape, like the pendulum that we did at one point in time, or a ball rolling down one hill and up the other side, then the displacement time graph is going to look like this. Velocity time graph is going to be a continuous straight down line, and acceleration is going to be negative the whole time. So the key to these is to remember that if your velocity and your acceleration have equal signs, then the object is in fact speeding up. If your velocity and acceleration do not have equal signs, then the object is slowing down. What I mean by not having equal signs is here, positive direction, you're moving in the positive direction, so your velocity is positive, but you're slowing down, so your acceleration is negative. So a positive and a negative are not equal, so you know the object is slowing down. Okay? So this setup of 5 graphs, the position, velocity, and acceleration, all versus time graphs, are something that you should be able to recognize for the test. Now, if we have a velocity time graph and we look at the area under the curve, remember that the area under that curve is displacement. The graph can be as crazy as we want it to be, or as whatever the indication is based on the object's motion. But from this graph, if we look in more detail, we would end up with this first equation from kinematics. And that gives us our delta x equals v naught t plus 1/2 at squared. Remember, this delta x is really the final position minus the initial position. So it really has an x minus x naught in there. So sometimes we write this equation as x equals x naught plus v naught t plus 1/2 at squared. The other equations that we can come up with, starting from the definition of acceleration being delta v over delta t, leads us to the second equation of v is equal to v naught plus at. This third equation here, where delta x equals v plus v naught over 2 times t, this thing in parentheses is actually your average acceleration. You would use this one most of the time if you have a case of your x and t looking like this. Then to find the average velocity, you just take the ending velocity and the beginning velocity, add them and divide by 2. Okay. The fourth equation is up here on the right, v final squared, which we've just been calling v up until this point, so I'm going to get rid of that final there. So v squared equals v naught squared plus 2a delta x. We did not actually derive this equation, but we could have if we really wanted to from another graph. I just didn't really think we had to. So how do you know when to use these? Well, we use equation 1, this one over here in red. We use equation 1 when you do not have a final velocity value. You don't know how fast the object's going at the end, so then you use this first equation. You use equation 2 when you don't know your displacement. You use equation 3 when you don't know what your acceleration is. And you use equation 4 when you don't have a time. So you don't know how long the object was moving or how long he was accelerating or positively or negatively. So this is sort of a summary of the things that you need to be able to do from this unit. Also included in this, but I didn't write anything down about it because you guys seem to be aces at it, are motion maps. So again, I apologize that I had to cancel class today, but I am not feeling well. So here's a brief summary of what we would have talked about today in a little bit more detail, and probably with an example or two from the review sheet. So please go ahead and start your review sheet. And if you have any questions on it, either email them to me, and we can either discuss it via email, or I will have another office hour sometime tomorrow or Thursday that you are able to get to. Bye for now.